Hi, my name is Anthony Nguyen of OSSM. My mentor is Dr. Dee Wu of the OUHSC Science Center, Department of Radiological Sciences. In my mentorship project this year was utilizing computer vision and machine learning to further understand human-computer interactions. But before I can delve deeper into computer vision, I have to pretty much explain what it is. So I can look at someone I've seen before and recognize that I've seen that person. I can remember a particularly graphic scene in a movie. Not because our brain is hardwired to remember those type of things. However, the brains of computers aren't hardwired to do those type of things. And the point of computer vision is to help computers see and understand and extract information from visual inputs like images and videos and camera inputs. And we see major applications of computer vision within the facial recognition in your laptop to help you sign in if you have that. Biometrics, so you can use your fingerprint to sign in on your phone, and things like optical character recognition to scrape words out of images or things along that line. And for our project this year, we wanted to look into applications of computer vision. So we wanted to perhaps try our hand at making an eye tracker, something that could track the position of your eye/pupil and locate where you're looking on at a screen as we're using math. So to track the eye, we decided to go for the pupil because it's the most darkest part of the eye and thus the most easily differentiable by the computer. So there's two ways we decided to look into this. First is utilizing color detection, where you look for specific pixels within the frame that are within the specific RGB value range. So if you see example on the left, it's kind of hard to demonstrate how it's doing the color detection, but it's just going through all the blue pixels and then calculating the average by calculating the average of the X and Y coordinates. Although it does work, it's very inefficient because it has to go through every single pixel in search of those specific pixels that are blue. However, the second method we had was using blob detection or shape detection. So for this method, we ran a mask over the video input, and this mask would differentiate all the blue pixels, causing them to be the only pixels there, making the rest black. If you can see by this top right frame, everything else is black except the blue. And then we checked for major contours where you see, and because it's the only shape there, it's easy to point out that this shape has the contours because it's the only non-black pixels. And from there, we calculated the moment of the intensity of the pixels and easily find the center. And because this is so much faster and more efficient, we decided that this is the method we wanted to use. So, we decided to run this over the basic camera input or forward-facing camera. And because I wasn't born with platinum blonde hair, which is easily differentiable from the other black pupils, however, I have black hair, thank you, mom and dad, it detects a lot of false positives. For example, my hair, my eyebrows, my glasses. But we solved this problem, at least temporarily, by just picking a certain frame of pixels, for example, right around here, this box right here, and zoomed in. And we could just have the eye be its own separate frame, and it detects the pupil. And from there, we can start detecting where it's looking at and the point of vision. So we first have to set up the calibration, and excuse the graph made on Microsoft Paint, but what we did was detect the 4 points, the 4 corners, and took pictures of the pupil as it was going through that. And then it ran a pupil, the images of the pupil and eye through an algorithm that would find out the coordinates of those pupils and then triangulate where you're looking at the screen because of it, like from that information. And here's a sample of the 4 images the computer took to analyze, as was 1, 2, 3, 4 for each of those corners. From there, we ran percentage from edge calculations. So in this sample is something I simulated. It uses the top left of 0, 0, 100, 0, 0, 100, 100, 100. And in this current sample, it says that the pupil is at 60, 25. So the math has it calculate it being 60 from the left out of the total 100, right minus left. So it notes that it's 60% away from the left side of the screen. And 25% away from the top side of the screen. So if this were to be my eye, if I was looking at the screen right now, it'd be approximately, I don't know if you guys can see my cursor, about like this area right there. However, there were some fundamental issues we had faced. For example, we were mainly locked in a specific field of vision because our eye was locked in this frame area that we set it from the zoom. So if your eyes were outside of the area, it wouldn't work because it'd say that your eye was, I don't know, 150% away from the left side of the screen. And that was actually a thing, you'd be looking at a wall. And it assumed that your eye would be at the exact same place during calibration in the actual eye tracking position point of view finder. Because all the calibration calculations are based around your eye at a specific area. And you can't move it at all if you want to have it be accurate. But that's hard to assume because people are going to move. There's nothing you can do to control that. So we set out to find solutions to our problem. And oh yeah, here's a video of it in action. As you see, the issues that we see is you moving at the screen. Sorry for the lag. But as you see, it went out of the frame, which caused an issue, and the eye kept on moving when it's only technically supposed to be moving the pupil. So it overloads the calculation, causes it to be very inaccurate. So the solution. Oh, and the next issue we have is that the math is linearly confined. Because in this, what I mean by this is that if your pupil of your eye was 60% left of the bounding box, it assumes you'd be looking at 60% left of your screen. It doesn't necessarily mean, it implies that there is a linear relationship between these two attributes, but that isn't necessarily true. There could be a logistic relationship, exponential, logarithmic. You can't assume it's always going to be linear. So our first solution to the first problem is to track the eye in movement. Previously, our goal was to track the pupil, and I'm sorry I've been interchanging the two words, but they're two different things. We have to track the eye movement alongside the pupil movement. So we have previously our frame to capture the eye and pupil was static, but now we have to keep it fluidly moving to ensure that the eye and pupil are in the relative center of the frame. And to do this, I utilize the IBUG 300-W dataset, which stands for Intelligent Behavior Understanding Group, made by Christos Sanganas and Stefanos Zafiria, sorry if I butchered those names, from the Imperial College of London. And with this data set and some additional modifications made to it, we can scrape 68 points from a face representing major facial landmarks. As you see in the screen, we can note that we can see the general jawline, we can see eyebrows, both eyes, a nose, and lips. And an application of this picture would be right here. Yeah, I applied this over my face around inside a general bounding box. And because we are searching for the position of the eye, right eye in this situation, we pulled from the points 37 to 42. If you want to deal with left eye, you can pull 43 to 48, but in this situation, just 37 to 42. And if we apply this tracking to my face in motion, here's a clip of it. This is also laggy. As my face moves across, it keeps the eye and the pupil in generally the same position towards the center, much better than the method we used beforehand of the static frame of capture. And hopefully your head won't be moving too much during this actual application of the facial tracker. But however, it'll just be generally small movements. And as a result, the program should be able to stabilize your head in motion and keep your eye and pupil in the general frame right here to do calculations on. And next, to fix the problem of the math being linearly confined, we set up a new calibration process. So it's similar to the old calibration process of how the computer would take photos of your eyes and run those images through the image processing to find the coordinates. But we do this two times, one to find the y-axis and one to find the x-axis. And this assumes that your eye isn't going to be moving, your pupil is going to be moving left to right as you're doing up and down calibration. But we can hopefully assume that that will be true, if not, it's too hard to worry about. And from this, we write down, it stores two sets of points. The first, and within these set of points, the first value will be percentage. For example, in this y, this will be 0% from the top, 25% from the top, 25% from the top, 50% from the top, 75%, and 100%. And it stores the non-static coordinate as a second value of the points. And also do the same for the x-axis. And because it has those two set of points, we can analyze data from those two set of points to form graphs. For example, this is a sample graph I made. This is like 0, 10, 20, 30, etc. And we use machine learning to run through multiple mathematical models of logistic, exponential, logarithmic, and linear regression to see which one forms the best line of best fit based from general average distance from points. And from there, we can use within the calibration a percent to coordinate scale. Because we already know what the percent is going in with the calibration, like I mentioned beforehand, but we don't know the coordinates, we can make an equation to calculate the coordinates from the percentage. Now, it's going to be generally inaccurate. For example, if this were to be 0, it goes into the negatives. But this is generally the best way to go about this for a general accuracy. Now, during the actual application of the eye tracking to find the point of view, the camera tracks the coordinates of the pupil, and we have to calculate that to get the percentage away from the left and percentage away from the top. And to do this, we can just run an inverse function from the percent coordinate scale to create a coordinate percentage scale. And by doing this two times, one for the y coordinate of where your pupil's at the moment and the x coordinate where your pupil's at the moment, we can generally calculate your area of your point of vision. I also apologize for not having a slide about this right now, but some future applications of this project could be going about perhaps replacing the eye tracking portion with the mechanical portion. For example, you could, I was looking at some CNC machines and having to override them and how they can move X and Y. So if you can set the CNC machine by overriding it to move X and Y and attaching maybe a scalpel to it or something to do surgical things with, you could perhaps use this eye tracking / CNC machine overriding to automate some retinal surgeries or things along that line. But that is all for my presentation for now. Are there any questions?
Thanks, Anthony. I have one question. So your system apparently ignores things like glasses. How is it able to identify your eye as opposed to objects that would not be an eye?
We generally have it zoom in to a point where it hopefully ignores the glasses, hopefully. But hopefully your pupils are, the frames, we're trying to find a way to work around frames. But right now, all we can do is just zoom in enough on the lens to ignore the black parts of a frame and just hopefully detect the pupil. But maybe we could find something to detect just something that's the area of a pupil, just like a circular shape. And because the frames of your glasses are hopefully not circular shape with a darker inside, they should be able to ignore that. But we're currently trying to fix that solution right now, bug fixing on
it. Dr. Givens asks, can it perform the processing in real time?
To do the calibration, it needs a little bit of time to calculate all the coordinate scales.
but to do the actual application of tracking what your eye is looking at, it should be able to do it in real time. Yeah.
Okay, great. Does anyone else have any questions or comments? All right. Well, thanks again, Anthony. Oh, Dr. Wu says it is a real-time processing. So